This section clearly lays out the core challenge. We're using the scikit-learn library's _cluster_optics_dbscan function for clustering. The function gives us three key pieces of information: cluster labels, which cluster each data point belongs to, or -1 if it's noise; reachability distances, how far a point is from its nearest cluster; and core distances, how far a point is from its nearest neighbor within a cluster. The problem asks us to interpret the results, specifically identifying noise points using a "min_samples" of 5 and a "she" of 0.05. Think of it as a detective puzzle. We've got clues, the output data, and need to figure out who are the noise points. The bad guys. In our dataset, this section provides important context. It highlights that the question tests our knowledge of how _cluster_optics_dbscan works and how to interpret the results. The optics, ordering points to identify the clustering structure, algorithm is used to find clusters in data, and understanding how it defines noise and handles the distance measurements is crucial to correctly solving the quiz. It's like understanding the rules of a game before you start playing. This section provides a systematic approach to answering the quiz questions. Each statement, A, B, C, and D, is analyzed individually based on a solid understanding of optics principles. It shows us a clear path to evaluating each statement's truthfulness. It's like a step-by-step recipe for solving the problem. This section gives us the final answers and explains why they are correct. It states that A, B, and C are true, while D is false. It gives brief reasoning, directing us to the previous steps for a detailed explanation. It's like the solution key to our detective puzzle. This step involves examining the results from the optics algorithm. The algorithm has given us three key pieces of information: cluster labels, reachability distances, and core distances. Now, we need to understand what each of these means and how they help us interpret the clusters. Let's dive in. We'll use this information to identify noise points and understand the structure of the clusters. This is where we decide which points belong to a cluster and which ones are considered outliers. These are the three main outputs from the _cluster_optics_dbscan function. The cluster labels tell us which cluster each data point belongs to. A label of -1 means the point is considered noise. The reachability distance measures how far a point is from its nearest cluster. Finally, the core distance tells us how far a point is from other points in its neighborhood. This is where the core of the optics algorithm happens. It's a complex process, but essentially, the algorithm uses the min_samples and she parameters to analyze your data. It then calculates the reachability and core distances for each data point, ultimately assigning each point to a cluster or identifying it as noise. The process starts with the input data itself, which is expected to be in a format suitable for clustering algorithms, such as a NumPy array or a pandas data frame. This step doesn't require additional elaboration, as it simply represents your raw dataset that is ready to be clustered. These two parameters are crucial for controlling how the optics algorithm behaves. min_samples determines the minimum number of points needed to form a dense cluster. she influences the way the algorithm connects points and creates clusters, with a smaller she value generally leading to more distinct clusters. The choice of these parameters can significantly impact the clustering results. This section presents the main quiz question. The problem statement describes using the _cluster_optics_dbscan function in scikit-learn to perform clustering and asks about how to interpret the output. It focuses on identifying noise points based on the algorithm's parameters and the output array values. This acts as a visual representation to depict how the optics algorithm functions. It visually guides you through the algorithm's steps, from data input and parameter setting to algorithm execution and, ultimately, output analysis and interpretation. Hey Vamsi, let's dive into the heart of this quiz problem. Line 11 presents the core question. It asks us to identify which statements are true about the output of the clusteropticsdbscan function in scikit-learn, focusing on noise point identification and interpreting reachability and core distances. We're looking at how the algorithm handles noise in the dataset. Hey Vamsi, let's dive into the heart of this quiz problem. Line 11 presents the core question. It asks us to identify which statements are true about the output of the clusteropticsdbscan function in scikit-learn, focusing on noise point identification and interpreting reachability and core distances. We're looking at how the algorithm handles noise in the dataset. This line sets the stage, clarifying that we need to evaluate 4 different statements, A, B, C, and D, concerning the meaning of the algorithm's results, particularly the labels, reachability, and core distances and the influence of the SHE parameter. It's all about interpreting the outputs of the clusteropticsdbscan function. This line sets the stage, clarifying that we need to evaluate 4 different statements, A, B, C, and D, concerning the meaning of the algorithm's results, particularly the labels, reachability, and core distances and the influence of the SHE parameter. It's all about interpreting the outputs of the clusteropticsdbscan function. Statement of focus is on the meaning of the labels array in the output. A labels value of -1 means that a data point is classified as a noise point by the algorithm. It's a straightforward interpretation of the labels. Statement of focus is on the meaning of the labels array in the output. A labels value of -1 means that a data point is classified as a noise point by the algorithm. It's a straightforward interpretation of the labels. Statement B tackles the interpretation of reachability distance. High reachability implies a point is far from its nearest cluster, hinting at it being a noise point or situated in a sparsely populated area of the dataset. Think of it as how reachable a point is from the densely populated areas. Statement B tackles the interpretation of reachability distance. High reachability implies a point is far from its nearest cluster, hinting at it being a noise point or situated in a sparsely populated area of the dataset. Think of it as how reachable a point is from the densely populated areas. Statement C deals with core_distance . A core_distance of 0 suggests the point lies very close to at least 5 other points. Since min_samples equals 5, making it a core point within a cluster and not a noise point, points with 0 core distance are central to a cluster. Statement C deals with core_distance . A core_distance of 0 suggests the point lies very close to at least 5 other points. Since min_samples equals 5, making it a core point within a cluster and not a noise point, points with 0 core distance are central to a cluster. Finally, statement D examines the role of the SHE parameter. The question is whether it directly impacts the number of clusters found. The SHE parameter, actually, influences the shape of the reachability distance plot that helps to visually separate clusters but doesn't directly control the total number of clusters that the algorithm finds. It is related to how the algorithm connects points, but the number of clusters is determined by the data's inherent structure and min_samples parameter. Finally, statement D examines the role of the SHE parameter. The question is whether it directly impacts the number of clusters found. The SHE parameter, actually, influences the shape of the reachability distance plot that helps to visually separate clusters but doesn't directly control the total number of clusters that the algorithm finds. It is related to how the algorithm connects points, but the number of clusters is determined by the data's inherent structure and min_samples parameter. This section introduces the core concept, interpreting the results of the optics clustering algorithm, specifically focusing on understanding the meaning of the labels, reachability distances, and core distances provided by scikit-learn's cluster_optics_dbscan function. The interpretation of these outputs is crucial for understanding the structure and characteristics of the data clusters. We'll explore what each output value represents and how to use it to identify noise points and cluster members. Think of it as learning a new language to understand the output of a powerful clustering tool. This section frames the core concept of optics clustering output interpretation within a multiple-choice quiz format. Each option presents a statement regarding the interpretation of the clustering output, testing the understanding of concepts like noise points, reachability distances, and core distances. This interactive approach helps solidify the learning by requiring active application of knowledge. This sets the context of the problem, stating that the optics clustering algorithm, specifically, scikit-learn's _cluster_optics_dbscan implementation, is being used. Scikit-learn is a popular Python library for machine learning, and _cluster_optics_dbscan is a function within it that implements the optics algorithm. The problem focuses on understanding the interpretation of the output from this function and identifying noise points based on specific parameters, min_samples and she . This statement explores the interpretation of the labels array output by _cluster_optics_dbscan . A label of -1 indicates a data point is considered a noise point by the algorithm, meaning it doesn't belong to any identified cluster. It's a direct and straightforward interpretation of the output. This statement concerns the reachability distances. A high reachability distance suggests that a point is far from its nearest cluster, indicating that it's isolated or sits in a low-density area. Hence, such points are likely noise points or situated in sparse regions. This statement examines the _core_distances . A _core_distance of 0 implies a data point is within the neighborhood of at least min_samples other points. Such points serve as core points for clusters, forming the dense center of a cluster. This statement focuses on the she parameter of the cluster_optics_dbscan function. The statement is incorrect because the parameter does not directly set the cluster count. While she influences the clustering structure and the shape of the reachability distance plot, it does not directly determine the number of clusters identified. The number of clusters emerges from the interplay of the data and the min_samples parameter. These are the three key outputs from the scikit-learn's _cluster_optics_dbscan function. Labels provides cluster assignments, integers for cluster membership, -1 for noise. Reachability gives the distances to reach each point from its nearest cluster, and core_distances indicate how far each point is from its nearest neighbor within its own cluster. Understanding these is essential for interpreting OPTICS's results. This refers to the ordering points to identify the clustering structure algorithm, a density-based clustering algorithm that's less sensitive to parameter tuning than DBSCAN. It excels in handling clusters of varying densities and identifying noise points effectively, even in complex datasets. The quiz focuses on understanding its output. This question is about understanding how the optics clustering algorithm interprets data. Specifically, it focuses on interpreting the output of scikit-learn's _cluster_optics_dbscan function. Optics stands for ordering points to identify the clustering structure. It's used to find clusters in data, even when the clusters have varying densities. The core concept is to identify core points, densely populated areas, and then connect them to build cluster structures. The input for the _cluster_optics_dbscan function is a dataset. The exact nature of this dataset is not provided, but it could be any dataset that would be appropriate for clustering analysis. Imagine a set of points scattered across a map that we want to group into distinct regions. The algorithm then works on finding patterns and groupings within this data. Scikit-learn is a very popular Python library for machine learning. _cluster_optics_dbscan is a function within scikit-learn that performs the optics clustering algorithm. This function takes your dataset as input and returns several key pieces of information, such as cluster assignments and distance metrics. It's like the clustering engine, doing the heavy lifting to separate data points into groups. The function's output contains three important parts. Labels integer for each data point, indicating the cluster it belongs to, or -1 if it is noise, reachability distances, and _core_distances distances. Reachability distance tells us how far away a point is from another point, taking into account density of the data. Core distance refers to how far away a point is from a significant amount of nearby points. Think of it as a point's influence on its surroundings. This output helps to understand the structure and density of the clusters that have formed in the dataset. This statement says that any data point with a label value of -1 from the _cluster_optics_dbscan output is classified as a noise point. A data point that doesn't belong to any of the identified clusters. This is because the optics algorithm identifies outliers as noise points. These are data points that are not sufficiently close to any cluster centers to be part of any cluster, based on the parameters given in the function call. A high reachability distance for a point means that this point is far away from the nearest dense cluster or core points. Imagine a single house far from a town, its reachability would be high. This could indicate that it is either a noise point or located in a sparsely populated area in terms of density or concentration of data points. This makes sense. Points in sparse areas are hard to group into clusters. If the core distance of a point is 0, it implies that the point is surrounded by at least min_samples, a parameter defining the minimum number of points required to form a dense cluster. Other points that are closer than the point in question, implying a dense region. It's a core point because it's surrounded by others, acting as the center of a cluster. It is a vital part of a dense cluster and not noise or outlier. The _she parameter in _cluster_optics_dbscan influences the reachability distance plot's shape, which indirectly affects the resulting cluster structures and how many clusters are identified. However, it does not directly determine the number of clusters formed. That depends more on the data itself and min_samples. It's like adjusting the lens on a camera. You change the perspective, but you don't directly decide how many objects are in the picture.